Good morning. Welcome to Krishna's classroom. Today we consider the problem of construction of new measures. The genesis of this problem comes from a method of integration that we often employ, namely by substitution. Let us look at the following problem. We want to evaluate integral a to b x dx 1 plus x square. Now you see that one of the methods of integration is through substitution. So you take a and b to be non-negative. So it's some interval, some positive. Now that is irrelevant. That we will talk about soon. So the traditional method is put y equal to x square when you have dy equal to dx. Therefore, this integral transforms to integral 1 by 2 that comes from here. X dx is replaced by dy and then 1 plus y. Now, the limits of integration for the new variable is from a square to b square. We take a and now this can be easily integrated because it is log 1 plus y. Then you have easy way of integrating. But what exactly has happened? See, the original interval over which you want to integrate is from a to b. Now we have transformed this, or we have used a new transformation y equal to x square. Okay, so let us take this half interval. So the transformation is, or y equal to x square if you use, see this r gets mapped to the interval 0 to infinity, and then a goes to a square, b goes to square. So it's a map from r to r. In fact, it's a map from r plus that is the interval. Okay. There you see that it's a one-to-one map. Why it is a one-to-one map? Because the function y equal to x square is a monotone increasing function. And it is manifested in the following fact that its derivative, y derivative is equal to 2x dx is equal to 2x, and this is certainly an increasing function, certainly positive for that is on the 11th portion. It is going to be from 0 to infinity. Okay. What has happened under this map? Under this map, see the original length of this interval is b minus a. Okay. So the length of now here we have got a new interval, that is a square b square, and the length of this interval is b square minus a square. So what have we done? We have introduced a new concept of length on the half line, which has been induced by the transformation y is equal to x square. Okay. So that gives some versatility. So in this, it's a new y space that in which you are playing the game instead of the x space, but from x space to y space, you have gone through a new transformation, and the interval AB gets mapped to a square b square, whose length is now b square minus square. Okay, right? Then what is this length of the interval AB? The length of the interval AB is what you call the measure of the interval. It is the Lebesgue measure of the interval, if you want to call it. Okay, and here the Lebesgue measure of the same interval of its image interval is b square minus a square. There is one more thing. Suppose you take AB. Okay. Suppose you take another interval. So you see that for all intervals a length is defined. That is the Riemann integration is based on that. Now here also for every interval a length is defined. But now the length of the corresponding interval here is something different. Okay, or we have changed the measure altogether. Okay, right? This can be looked upon. See, b square minus a square can be looked upon as a new length that you attribute to the interval AB. It just happened through this transformation. Okay. How have we achieved this? See, this we have achieved through this kind of transformation. So if you look at, this is the y variable, this is the x variable. Now you see that the transformation y equal to x square, the graph of the function is something like this. Okay. So the mapping that takes place is this. The interval AB is mapped to a new interval, a square b square. This is the new interval. It's the new image that you. This interval goes to this interval. Likewise, every interval here gets mapped to another interval. But now the interval, the image, the length of the image is going to be totally different from what is not equal. One more thing is that in our original measure, if you take the interval 0, 1, just translate it, what will happen? You will have the same measure. Whereas, you see that if you take this a square b square, suppose you take this one and translate. So you have a plus alpha, b plus alpha. Let's translate. Now you take the mapping of this. Where does it go to? Under this transformation, it goes to a plus alpha this is the translate of this interval gets mapped to what is the length of this interval? The conventional Lebesgue measure of this interval is b minus alpha is equal to e square minus a square. Now you have got this alpha square cancelling out, but you have an additional term, namely 2ab minus 2ab alpha. Okay. Sorry. This b square this is equal to b square minus a square. Now 2 alpha b, right, plus 2 alpha plus alpha square minus alpha square cancels out. Okay. So what happens? Okay. Alpha is positive. Now it's going to be a change. Now you see that the new the image of the translates is going to be totally different. So this is not equal to e square minus h. So what happens is the image of the same of two different intervals of the same length under this transformation is different. So you are inducing what you can. Another way of understanding this is that we are taking the interval 0 to e, and then you have the original measure a to b minus a. Now, by this transformation, we are inducing or we are attributing a new length on this, okay, which has all the properties of a length, except that the translation is set. Okay. Of course, this difference, and it varies from, suppose you take two intervals of the same length like 1 to 2 and 5 to 6. Okay. Their images you take, they are going to be different. 1 to 2, the image would be 1, 2, 4. So the image has length 3, okay, whereas it's the corresponding interval that we have taken 1, 2 and 5 to 6. Originally they have the same length, but what happens to this image? So you have 55 or 36. It's about 11 units that you have, whereas here it is 3 units. Okay. This goes over to 3 units, whereas this goes over to some new interval, 11. So there is a change in the or you rig with the Right. And in fact, what you introduce is a new density that you attribute to the interval, so that there is a change that is there in the length of the point. So that's our background. So what does it happen? So here you see that you have introduced y equal to x square is a monotonically increasing function, which this change essentially facilitates the transformation of the interval of the integral into this, and these two integrals have the same value, but this is, this is a standard integral which you can easily evaluate, whereas this is not something standard. Okay. So what have we done? In the integration, now we are integrating something with respect to d of x square. Okay. A function here, d of x square. Right? Now you have changed the measure of intervals in that case. That is what has happened. And this is what is happening in the Riemann-Stieltjes integral. So Riemann-Stieltjes integral is a generalization from the Riemann integral, and the integral is of the form integral d alpha, where alpha is a monotonically increasing function. So that what happens is alpha derivative is positive or even greater than 1. Okay. Right? So now you see we have all sorts of possibilities by introducing a non-negative function which may be 0 on some interval. There what happens? Suppose the function is 0 on some interval, it is still a monotonically non-decreasing function. Okay, and you see d alpha on that portion is going to be 0, or in other words, there is no contribution to the integral coming from that. Okay, so this is one of the differences that you have, or it is quite possible that on R, if we introduce a new measure using a monotonically increasing function, now you can even make some of the intervals to have 0, or lot of versatility can be brought into the integration using this process. Now I am not going into the details of the Riemann-Stieltjes integral. This leads to now you see that if alpha is such a monotonically increasing function, assume alpha is also smooth, so that alpha derivative exists. Okay, if so, what happens is integral a to b alpha d alpha equal to integral alpha a, or you have, see, alpha x equal to a, and alpha since alpha is monotonically increasing, the roots are going to be again keeping the same order, so it is going to be some alpha inverse, or or the corresponding to psi, some interval psi to beta of alpha derivative dx. Or in other words, you can avoid confusion, we can write it this way. We write it this way. Suppose this is from integral alpha a alpha b of d alpha equal to integral fusion measure. Okay, so you integrate this and then compute the length. Okay, right. So you see that this is the sort of relationship that emerges with this transformation going in. So Riemann-Stieltjes integral is a generalization which even allows some intervals to have zero measure. Okay, whereas the original one we are using, so the original one is essentially this y equal to x. You take this function and then dy equal to dx. You are not changing the transformation. The transformation you are not changing the length of the interval. Whereas in a general scenario of alpha a monotonically increasing function, we are changing the length of the interval. So there is more versatility that what have we done? We have, through such a transformation, defined a new length for the same interval. Okay, right? So on the same interval, we are introducing a new length. As I said, is this. This is the function y equal to x square. Then see that if you take this interval, this is a slightly bigger length that you have introduced. On the other hand, suppose you were to introduce something like this. This is again a monotonically increasing function. So you take alpha, something like this. Then what happens? On this interval, you see that the length is redefined. Depends on the slope of this line. And suppose you take this interval, it has a positive measure here, whereas the corresponding measure that you have is 0. So for this, from this part, if you take a function f defined on this interval and integrate, then there is no contribution coming from this part at all when you use. When you take f d alpha, see, you are not going to get any contribution from this part of it. So something like 0 to right? Or 0 to m something. Then you see that from this portion there is not going to be any contribution coming to the integral at all. Okay, so there's a possibility that certain intervals, so all the intervals have a different all intervals traditionally of the same length have different measure, or we have successfully introduced a new concept of measure. Okay, so from the classical measure of length of an interval, that is the Lebesgue measure, you can introduce a new concept of measure through by putting in between a monotonically increasing function, the real line. Okay, now we are going to generalize this. Okay, in the general scenario. So what have we got? Okay, let me just now start on this. See, I have what you call the set X with a sigma algebra on this and a measure. This is given. Right? So if you take any subset A, any subset E belonging to M, that means any measurable subset of X, it has got a length attributed to it, which is mu. Is the length attribute, or what you call the measure attribute. This is what you call measure. So you have a set X over which there is a sigma algebra of what you call measurable sets, and then on that you have defined a measure, which is we defined a positive measure by introducing a non-negative measure, non-negative function from mu from infinity, which is countably additive. Countably additive, and for some it's an extended real value function or non-negative value function, and for some A belonging to mu of A is finite. Now this is what we considered as a measure on the sigma algebra that you have defined. Now the question is, as we did by rigging the content of M, not really the content of the M, the measure of the content of the M, can you introduce a new measure? Okay, this is the given basics, and what we are going to do is we are going to rework the content, the measure of the content of elements of M. Okay, and then check whether it is a measure. Okay, so this is what is contained in the following theorem. So what one does is this. You to take a E belonging to, you have mu E already. Okay. Now we take the function chi E. Okay. That means the function that is identically equal to 1 on E and elsewhere 0. So you define this one, integral over x chi E. That will give you mu of, okay. But suppose we uh, we take the following. Take a, let S be a non-negative measurable function simple function on x. Then what you have? You have S x equal to sigma ai, where ai where ai to the set on which uh, where suppose let range of S is a map from x to that is which is contained in then you take AI S inverse of alpha I. If alpha 1, alpha 2, alpha n are different, that is alpha I not equal to alpha j whenever I not equal to j, then okay. Now you can define this function S as now you see that the function S is chi AI takes the value 1. Therefore, on AI, S takes the value alpha I. And you get AI intersection AJ empty whenever I is not equal to J. Therefore, this is the representation of the simple function. Now we prove the following theorem. What we prove is this. Suppose you have got E. Then you define the following. Integral over E SB. Okay, that we shall see what exactly it is. We'll work it out. Okay. The theorem says that this particular phi d defines a new measure on the sigma algebra. So theorem that not negative measurable functions, measurable simple functions which means the both S and T takes only finitely many values. The range of S and T is finite. For any E which is measurable, we define Also integral over x of s plus t g mu. Both s and t are non-negative measurable simple functions. This is equal to integral over x So suppose you take, suppose on E you take the function to be equal to 1. In that case, what you get? You get mu of epsilon. Let us prove this here. Quite easy. Routine computation. Let AI, where AI is a set of all x such that for I equal to let etc. be disjoint measurable we assume EI is to be disjoint. That is, you have that is also there. Now we use the countable additivity of mu. We have phi of E is defined as, when this is the sum that we are talking about, sigma I equal to 1 to n. Alpha I, when you are restricting to E, then this is going to be measure of, this is the definition of the integral, measure of E. Now we further define this, okay, which is equal to, okay, what we also define is, let E be equal to union of EI. then phi of E, you have this result, and this being the union of PIs is which are mutually disjoint. What we have is this. This is equal to sigma I equal to 1 to n alpha I sigma r equal to 1 to infinity mu of here. Okay. Because here we are writing AI as the countable union of AI intersection ER. AI is assumed to be measurable. E is ER is measurable. Therefore, this is measurable. So, mu of this is well defined. Okay. And therefore, you see that since mu is a measure, you have intersection. See, mu AI intersection E would become sigma mu AI intersection ER, where R running from 1 to E, where E is equal to, I'll use the same expression, R to ER. That's it. Isn't it? Okay. This is equal to, now we can interchange the summation. It commutes actually 1 to infinity sigma n alpha I mu of AI intersection ER this is it. What is that? This is equal to one to infinity yeah, look at the definition. This is alpha I mu AI intersection E. So AI intersection ER is coming there. So you see that this is equal to summation of R equal to 1 to infinity phi of, since phi of ER equal to so you have on one side you have this A1, A2, etc. AN. On the other side you have got these ERs. Okay. Now you are looking at that, you are taking ER and how many of these AIs intersect, that you take into account, and that's what's coming here. Because you are summing over from I to N and then summing from R to. So this by definition, this part would give you simply phi of, yeah. So you get phi E equal to sigma 1 to infinity phi of theta. That is phi is countably therefore you have, of course, you know that phi is greater than or equal to 0. Phi is countably additive. And further, what you get is this. The empty set. This is equal to 0. So that phi is not identically this is quite easy to see because you replace in place of phi, in place of E, you replace by phi. You get this result. Because you know that mu of an empty set is Q. Okay, so that completes the first part. That phi is a next we prove the other results. That means S is equal to alpha I chi of let be distinct values of theta. So we are now trying to add up this phi with or S with P. Let such that define we have now two sets of two collection of subsets, namely AIs, N of them are there, and BJs, M of them are there. Therefore, you get EIJ, which is M into N, Mn types of this are there. So, I belongs to N. J belongs to that is EIJ. Then you define this or integrate this. This is equal to alpha I plus beta j times mu of Vij. And Vij. Therefore, what you can say is that the second statement of the theorem, holds with now x is the disjoint now by the first half of the proposition. Theorem, namely phi equal to phi equal to integral over E S dV. Okay. So that will give you or in other words, what you are getting is this: for any E, suppose integral over E d d mu equal to psi of E. This is defined like phi. Then what you get? You have phi plus psi so the sum of measures is again a measure. That's what it means. Phi plus psi of phi plus in other words, it's another measure. Okay. So you can keep manufacturing new measures by choosing what are called non-negative simple measurable functions and then working out the integral. So this is the formula that phi of E is equal to integral over E. This is the definition. Yes. What you this is the new measure that you okay. Psi is so phi plus psi equal to phi plus psi. Okay, so I think concludes the today's lecture. And now hereafter we will be looking at what are called the convergence problems. Thank you very much.